Welcome to today's webinar, What It Takes to Implement a Successful Injection Project. Thank you for taking the time to join us today. I'm Sue Bruning, Vice President of Marketing and Communications here at Cascade, and I'll be your moderator for the broadcast. In today's webinar, environmental remediation technology expert Eliot Cooper provides insight into critical planning steps for your next injection project. We do have handouts available for you to download at any time during the broadcast. If this is your first time attending a Cascade webinar, I'd like to extend a very special welcome and help you get to know Cascade a little bit better. Cascade Environmental is a field services provider that offers drilling, site characterization, and remediation. Everything you need from project concept to completion. Our remediation team has the nation's largest fleet of equipment, the deepest bench of technologies to choose from, and leading industry experts who can help you get the results you need. Experts like our presenter today, Eliot Cooper. Eliot is Cascade's Vice President of Technology. His environmental remediation career spans over 3 decades. He specializes in injected remedy delivery, remediation design support, characterization of VOCs, and tackling complex sites by combining multiple remediation technologies. So without further ado, take it away, Eliot.
All right, thank you, Sue. So next slide. So I thought starting out today, we might want to define what a successful injection project is. And then when we're complete today, we may want to revisit this definition. But these are some of the bullet points I look at when I look at a project as being successful. For example, was it a design optimization test or a pilot test performed to establish full-scale design specifications? How did the startup go? Was it uneventful? Were all the amendments injected and was the inventory reconciled? Were there any safety issues? There should be none. And if there were near misses, they should have been reported. Were all the amendments mixed properly? If there was troubleshooting required, which is not that uncommon, was it effective? Did the injection perform? Were they within the flow and pressure specifications that were documented? Was the vertical and lateral distribution of the amendment verified? And also very important, was the project completed on time and budget? And as the last one, I have contaminant treatment expectations were realized. So this is one I think is open for debate, speaking as an injection contractor. And while we can control the distribution of amendments, there's a lot more into successful remediation that goes beyond the injection component. So there I would say that that's open for debate. So next slide. So as you know, the ITRC did a whole team effort on optimizing injection. They did just have a webinar this week on that subject. But I still think, Houston, we have a problem because what ITRC overlooked was really getting into the nitty-gritty of how the amendments are injected and best practices and what should be the recommendations for optimization. So that's what I'm going to address today, the injection component, and try to add to the optimization document. So next slide. So we've had a few webinars this year about optimizing in situ remediation. We came up with a methodology. We've talked about various components of this methodology steps. We spent a lot of time on the characterization side. And but today what I'm going to focus specifically on is the injection of liquids or fracturing of solids into the subsurface. So what are the components of an injection project? Now don't worry about the small lettering here because I'm going to break one of these down specifically. But what we look at is the component itself at a high level, in this case safety. We look at key items related to that component and whether or not they have a direct or indirect impact on injection performance. And so things we're going to look at today are safety, direct push drilling, mobilization and setup, amendment handling, and reconciliation, water management, mixing, pumping, performance monitoring and reporting, shakedown distribution testing, and troubleshooting. So what do I mean by direct versus indirect? So direct means that it impacts on achieving the required distribution and contact with contaminants. So that's obviously very, very important. Indirect means that the impacts will result in losing focus on achieving the direct impacts, and that'll also indirectly impact performance. And if you've been out in the field on projects, you'll be aware of these indirect impacts that ultimately impact the overall performance of the whole injection project. So let's talk about safety real quick. I took a DuPont safety training course years ago, and I always remember the one message: if you can't manage safety, you can't manage your business. And I think in our industry is, if you can't manage safety, you can't manage a successful injection project. So I think they go hand in hand. And so numero uno for us is always delivering these projects safely. And so there's a lot of components that go into that. There's the health and safety plans, the site data safety sheets, there's JHAs or JSAs, there's standard operating procedures, there's PPE requirements, there's a spill prevention control countermeasure plan, there's process flow diagrams. In the field, we have tailgates, inspections, near miss reporting. There's a whole component of training, and then there's a specific requirement under OSHA related to short service employees. So one of the things I think that's important in any project, especially when you look at the safety, understanding the safety risk, is to have a good process flow diagram of what's going on in the project. This is an example of an extraction injection system that we put together for a project, and really outline all the components from extraction of groundwater to carbon filtration to dilution with amendments to anaerobic water setup to actual manifolding and injection into numerous injection points. So if you're going to have a site-specific safety plan, you really have to understand the process flow that's going to be implemented. Standard operating procedures. This is just one example of a standing operating procedure. This is caustic activated sodium persulfate for implementing through direct push. And you can see here we address a lot of different aspects of the project, from mixing to drilling to injection to abandonment to distribution verification, spill control, et cetera. So standard operating procedure for all aspects of the project are required if you're going to have a safe implementation. Also, job safety analysis. This is just a list of the ones we have just for the injection side of our business. And you can see there's a lot of them here. And we have things from fueling operations to DPT operations to grout mixing, chemical injection into to you name it. So we have a JSA for every aspect of the project that folks need to be trained on and understand to make sure that safety performance is going to be 100%. So just some pictures here to represent some of these safety concerns. Spill prevention and response. So obviously, in a lot of cases, most of the chemicals that we work with, our customers, the regulators, the public don't like to see them except in the boring location or on the injection system itself. So here's just an example of a sticky mat that we use to control any type of spill or surface runoff that could enter into a storm sewer. So there's a lot of components that go into a spill prevention plan and a lot of equipment that you've got to mobilize to the site. And this is just one example. Spill containment. So obviously secondary containment of amendments is important, especially when you're unloading tanker trucks into tanks. In this case, upper left, we've got calcium polysulfide for hexagon treatment being loaded into a 6,500 gallon Baker tank. On the right of that, we've got 300 gallon totes of 25% caustic, which is an activator. Below that, in secondary containment, we have totes of 4% sodium permanganate. And then even these mini secondary containments where we may have drums of material close to the injection systems. Other things to look at is high pressure. A lot of projects we work on have work under high pressures, especially when we're fracturing in solid slurries like ZBI into tight formations. And one of the things that's often overlooked is the rating of the whip checks that are used should any of that equipment get loose. And so it's really important to make sure first you're using whip checks and that they're actually rated for the right pressure applications they're going to experience. Residential injection. So as you know, the plumes really don't care what's above them. They go where they want to go. And so you really need to have a very robust health and safety plan if you're going to be injecting in neighborhoods, on public streets, etc. This is just an example of injection of potassium permanganate on a TCE plume over a new housing development. Here's just another example. This is a persulfate, activated persulfate injection under a condominium building, treating TCE in the Vado zone. So residential injections, even though every project requires the same level of attention from a safety perspective, there's even a heightened focus on the public in these applications, and plans have to be developed accordingly. Compatibility of chemicals, something that, you know, if you've been in the industry a while, you understand this, but you know, it's often new projects people forget, but we work a lot with sodium persulfate and different activation chemistries. It can be handled safely, but things we have to worry about is high pH. On the left, you can see we're measuring pH of a 12 and above of a caustic activation. In the middle, that's a piece of pipe that was exposed to iron activated persulfate. On the right of that is a mixing of ferrous sulfate, heptahydrate, the activator. And then the problem we have with the high pH, we can generally flush our rods out and really not experience much corrosion. But on the other hand, with the low pH, there's an example of how the rod threads can be destroyed pretty quickly, and you end up with all kinds of problems moving forward. PPE for these type of chemicals, very critical. You can see here, while this may be uncomfortable for our operators, especially in hot weather, that this is the type of PPE required when you're dealing with persulfates or peroxides and caustics or permanganates. So PPE is often overlooked, or there is an attempt, but it really doesn't provide full protection. And so this is something to also make sure you're having implemented on your projects. Transport of amendment. Now this is a project I consulted on in Denmark, so I haven't seen this level of craziness here, but in this case, the client needed to get the sodium permanganate 40% to the project site. And so the client decided to transport it in their own little minivan. And you can see there the back of the van was about 4 inches off the ground. So very unsafe. The ability to get that full tote out of the van with a lift was also a very hazardous operation. So don't underestimate the transport and unloading of chemicals. Generally, that's the highest risk we experience in a project, is that one phase. And it's really critical to overkill how that's going to be managed. Also, you can have leaking drums that come to you during delivery. And obviously, that's going to be an issue. You've got to have a contingency plan and a hazardous response team on at the ready to come in, put that leaking drum in a salvage drum and take it back to the manufacturer. And this does happen. A lot of pallets have nails in them. So we've seen this more often than not. Now, my favorite subject, hydrogen peroxide. I still see it being applied across the country. It's a great technology for petroleum hydrocarbons in transmissive zones, sandy zones, but there's a lot of safety considerations in dealing with hydrogen peroxide. There can be very high temperature increases, and so you've got to be able to monitor the subsurface with thermocouples on the left and on the right. You've also got to be able to monitor for explosive vapors, as well as vapors in the workspace. Below, there's a picture of a drum being vented, used as a vent container off an injection well. So more often than not, you're going to get high pressure when injecting peroxide or catalyzed peroxide, and you're going to have to vent that material in the drum. And you're also going to have to figure out what to do with that drum. And then most importantly, ball valves. All ball valves that come in contact with hydrogen peroxide have to be vented. If some reason that peroxide gets contaminated with a small amount of dirt, it's going to react and it's going to blow that ball valve if it can't find a pressure relief. So these are some key aspects when you're working with peroxide. The other thing I'd like to point out is I don't recommend injecting hydrogen peroxide at active gas stations. The MSDS and the labeling on the containers say incompatible with hydrocarbons. And so I just don't understand why one would attempt that, but I still see RFPs coming across my desk for these type of applications. So hydrogen peroxide is one to be very careful with. Here's just an example to the right of what happens if you inject hydrogen peroxide too fast or in a very contaminated zone. It's an immediate uncontrolled reaction of steam and surfacing. So like I said, if you're going to work with hydrogen peroxide, your safety antenna has to be way up, and you're going to have to overkill all aspects of the project. So let's move on to mobilization and setup. A lot of things here that have to be worked out: footprint of the injection system, deliveries of amendments, rental equipment, secondary containment, exclusion zones. How often do you have a site where the public walks right to the middle of your site? It's not that uncommon. Scheduling, work at night or day, what the work hours are going to be, and then there's obviously DOT restrictions that impact how much work can be accomplished over a certain time period. So here's the checklist we have developed to work with our clients before we move to the site, because in RFPs, proposal is requested. We submit an RFP, there's some site information, there may be some questions back and forth, then an award decision is made, and then you may sit on that project for a month or two before it's time to move to the project. So that's all the information you have, and now everybody's expecting to show up and be ready for prime time. So we've developed this pre-mobilization checklist that you can download that gives you the ability to go through all the details so we don't have any surprises mobilizing to the field. So we break down the checklist into just a high level project overview, what information was available. We then go to the actual scope of work, making sure that hasn't changed. More often than not, the scope does change from the time the proposal was submitted till the time we move to the field. Then we get into the actual injection itself, and what we have here is primary pieces of equipment, contingency equipment, first set, which we should have at site, and then a second contingency that we may have to bring in from offsite. And so we look at all the different types of equipment and making sure we're all in agreement with the client on these, so there's no surprises. So we look at the pumps, the transfer pumps, the injection tooling, the types of injection hose. If we're going to have packers, a whole bunch of considerations related to packer and packer safety, type of direct push rigs that are going to be used, the type of injection rig, including the pumps, the mixing components. Is there a change management requirement because the rig's moving into a different type of service? Connections, mixing tanks, all kinds of equipment issues that are going to have to be spot on as we start up the project. Any of these things that aren't in our client's expectations is going to create a delay in startup, and also, like I said, an indirect impact on results. And then we look at all the plumbing issues, as well as distribution verification. Are we're gonna have to verify distribution before we start, which is a good idea. The plumbing, the fittings, the pipes, the ball valves, the pressure gauges, the flow meters, pressure relief valves, setting of pressure relief valves, all those types of things are going to be important to work out before we show up at the site. And then finally, we get into logistics. And now we're looking at all the things like utility, chemical handling, subcontracting, power, water, rentals, spill control, etc. So a lot of logistical things have to be worked out before we move to the site. And then finally, how is everything going to be documented? How are we going to track the inventory? How are you going to track injection performance? How are you going to track safety and spill documentation? Is there any change management documentation, training records, etc.? Unique safety considerations for a project. So let's spell those out ahead of time so they're not surprises. And then there's all the issues related to crew logistics in terms of who's going to be your operator, what's the schedule, how are they going to get there, what are the DOT constraints. And then finally, the project challenges. So is there anything unique about the project going in that we all need to know about? So this is really critical. A lot of times folks seem to hide some of the challenges. That's not going to help anybody. Let's define if we're next to a storm sewer or a utility and get that figured out ahead of time. Anything that becomes a surprise in the field just ends up slowing down the project and impacting the overall performance.
Eliot, we'll pause here and I'll just want to remind the audience that we do have some handouts available, and the injection pre-mobilization checklist is one of those downloads. So feel free to jump in there into the handout section and download at any time.
Yeah, thank you. Yeah, I know there's a lot of information there. We put a lot of thought into those based on hundreds of projects. And if you go through the checklist, you've got a high probability of the mobilization and readiness being on target. So like I said, we're just trying to prevent surprises. So here's a surprise. Hey, we got to work in mud. That was not disclosed in the mobilization. So eliminating surprises is a critical aspect to starting a project successfully. So let's look at amendment handling and reconciliation. So I'm going to start going through these a little quicker because all this stuff will be available for your review. But we look at the handling of amendments. Are we going to be transferring liquids, or are we going to be transferring bulk liquids or bulk solids? What kind of packaging are we getting? Totes, drums, super sacks, tankers. Let's make sure the inventory is correct before we start. How are we going to store this? Or is there compatibility issues between the chemicals? And then when we're done, how are we going to decon and take care of the containers that are left over? So here's just some examples of unloading. Obviously, you'll see a lot of forklifts in our proposals. We'd like to use these extendable forklifts. They're more convenient. In some cases, they have to be four-wheel drive. But in a lot of cases, we're unloading totes, we're unloading super sacks, we're unloading pallets of drums. So like I said, this is probably the highest risk aspect of any project, but often overlooked. So be very diligent during the unloading and transfer operation. Let's look at mixing. So mixing is obviously important. We want to get a uniform mixture of the amendment into the subsurface. And there's all kinds of mixing. There's inline, there's batch. We can mix in various tanks from 75-gallon tanks to 6,500 gallon tanks to frac tanks. We've got to mix liquids or solids. In some cases, we're going to inline dose amendments like dihelicoides. We've got to look at overflow protection in tanks. We may want to pulse mix or pulse inject two different reagents. We've got filtering to look at, both to prevent plugging of flow meters as well as to prevent plugging of our injection tools or injection wells. When we're mixing, we've got an employee issue of ventilation that we have to take into account, and also air monitoring. For example, when we do calcium polysulfide, we've got strict air monitoring requirements for sulfides, so hydrogen sulfide. So these are different mixing systems. The upper left, that's getting intermodals of emulsified oil and then transferring those into 250-gallon totes. We do that a lot for secondary line of evidence on volume. So if we're going straight from a tank into the injection system, if that flow meter's off, we can be way out of whack pretty quick. And so we like to have those totes because we can always count the amount of totes we have injected in a day. We can also mix in totes. We can mix in stainless steel tanks, and we can mix in large tanks like these Baker tanks or frac tanks. A lot of times we're going to be working with bulk solids, and in large projects, it's a lot safer and cost effective to deal with bulk solids than small containers or bags. And this is just an example of a bulk unloading system for sodium sulfate, Persulfate, that we then transfer over into a tank and recirculate and get to the design concentration. Solids mixing is also very important. If you don't get a uniform mix, you can plug your pump, you can plug your injection line, you can plug the injection tool, and that's going to impact distribution in the subsurface. This is just an example of a ZVI guar mixture. And it needs to, obviously, there needs to be a standard operating procedure for that and some Q&A to make sure that you're consistently injecting the design concentration without a lot of suspended solid settling. So this is often overlooked, but it's very important that your solids are mixed correctly. Water management. So obviously we need water to dilute most of these chemicals. So we're either access hydrants, we're going to extract groundwater, or maybe have to turn this water anaerobic. We've got to store it. There needs to be lead times in some cases to make sure the water is ready. So to support the injection performance. Sometimes we have to buffer the water because of bacterial considerations in terms of pH. And sometimes we have to dechlorinate, excuse the typo there. So obviously fire hydrants, we use those a lot. Sometimes we can hook right up to them, and sometimes we've got to transfer through a water truck. We've always got to get the backflow preventer and meter from the local municipality. If that's not handled correctly, there can be days of delay at a project start. So while it's standard operating procedure, I've seen projects get delayed just on that aspect alone. Also, we need to know how far that hydrant is from what we're trying to fill up and compare that to the hose we're going to use, because sometimes we may be 1,500 feet from an injection setup, and we've got to look at the pressure drop through the hose to make sure that we can still get the flow rate to meet the performance and mixing that we're anticipating. Anaerobic dilution water. So this is pretty common now with bioremediation of chlorinated solvents. This is kind of not a large project case where we needed 4 frac tanks to create the anaerobic water required to support the overall injection performance. So in some cases, it's not a big issue because we may be just making anaerobic water to blanket the helicoides inline, but in some cases, and also considered best practice, all the dilution water should be turned anaerobic. So a lot of times we're moving liquids across public right-of-ways, roads, etc. So we got to protect those, and these are just some examples of ways we can protect injection hose on the left or fire hose on the right. You've got to plan for that, and it can be not become a major logistical issue for you. So now pumping, and actually pumping is the heart of all this. I mean, we're basically pumping amendment into the subsurface. So we've got to know the pump type. We need to know its pressure and flow curves. We need to know if there's some calibration of the flow meters. Can they handle liquids and solids, and what size? Are they compatible with corrosives? How are we going to power those? Hydraulically, electrically, or compressed air? Do they need pressure relief from a safety perspective? Are they variable speed pumps, or are we going to recirculate to control overall pumping rates? And are we going to be able to manifold? So I just want to go over these pumps real quick. You can look at the details later, but these are the go-to pumps that are used in the industry. One of them is the hydraulic Moino pump or progressive cavity pump. It's capable of liquid and solid slurry injection. You'll see a lot of drilling contractors use these for grouting, but they can also be used for injection of liquids and solid slurries. The other pump that's gained some acceptance over the years is the positive displacement pump. These are electrical, usually run electrically, and one of the major manufacturers of these is Hydrocell, and these can inject liquid and solid slurries. They do have a high pressure rating, so they can go up to sometimes up to 1200 psi at 30 GPM. But it's important to have pressure relief capabilities on these pumps, because if you're pumping through hose that's 250 psi rated, and this pump hits a blockage, and it's going to go right up to 1000 psi. So you've got to be able to have pressure relief, key safety aspect of using these type of pumps. And you have to know where to set those pressure reliefs, and you have to test that. A lot of folks have seen the air diaphragm pumps. They're simple to operate. I see a lot of them used for injection of liquids into injection wells. So they're out there. We generally don't use them, but they definitely can get the job done. A little concerned of the pulsing, not as easy to control, but they're still a go-to pump in our industry. Centrifugal pumps, they're obviously very attractive as well. They can be stainless steel. They have high flow rates, but their pressure curves are not very conducive to higher pressures. So as soon as they see high pressure, their flow rates drop down very quickly. So on the right is kind of a super centrifugal pump that we use, stainless steel. And we use this for projects where we're injecting high volumes. So typically with these, we can get up to about 200 total GPM. And these do have high pressure ratings, so they really are not that impacted if we start to get some back pressure. And then there's the piston pump. This is an electrical piston pump for solid slurries like zero valent iron and guar. You'll see these used a lot for EHC, peroxide projects, but they basically are double pistons. They can handle the abrasiveness of the CVI, and they can work at, this one can work at 55 GPM at a high pressure range of 2000 PSI. So piston pumps are very common for solid slurries, and I'm sure you've seen those out in the field. So just one thing on compatibility, and you can find these type of charts on the internet, but all these pumps have compatibility with certain materials of construction, and you just have to make sure that the pump is going to be compatible. For example, with potassium permanganate, with a mono pump, we have Buna stators that we've used in the past. Those degrade very quickly with permanganate and are not recommended. And so we switched to EPDM. So all the working components of a pump need to be compatible with the amendments you're working with. And actually, Peroxide has done a good job with sodium persulfate, because it is can be a very corrosive material, and they've gone through a lot of detail on the different activation chemistries and the type of materials of construction that can be used for a wide range of persulfate, iron persulfate, caustic persulfate, et cetera. So you'll be able to see this one in more detail. But as a general rule, most pumps we're using in corrosive environments are going to be stainless steel. Filtering. So one thing we don't want to do is plug flow meters. And for various reasons, we can get some solid material in the feed tanks, and we want to screen those out before they get into the flow meters, because when they plug, they have to be taken offline. Sometimes the construction of the integration of the flow meters may not be that conducive to pulling it out very quickly. So filtering before the pump, and then post pump. So certain solid slurries, their solubility is not, is low. So for example, potassium permanganate, as a general rule, we don't inject above a 2.5% concentration. And even with that, we want to filter out the permanganate as it goes into the injection point, in this case, injection wells. And you can see there, we've got some sock filters, and you can see even with good mixing and a 2.5% slurry and at room temperature, we're still going to pick up some undissolved potassium permanganate. Manifolding. So manifolding is key to the cost effectiveness of injection. I think one of the downloads you have is a calculator you can use to manifold. Calculate if manifolding is going to provide a good return of investment for you. But generally, most of the manifolds we use are all stainless steel, so they can use for multiple chemistries. On the left is just a manifold where we're able to dose in dihalococoides inline to the system. In the middle is an example of a manifold where we had to put rotometers on the manifold because we were injecting at very low flow rates that were below the limits of those flow meters. And on the right is a more sophisticated manifold where we're actually dosing in diluted substrate as well as a lot of anaerobic water, and at the same time dosing in dihalococoides. So manifolding is a key component to optimizing injection, and generally, if your flow rates are going to be limited by pressures, then you can manifold to get your total flow rate up and still keep the project cost effective. Or if you just need to get millions of gallons in the ground, manifolding to multiple points is going to make a lot of economic sense. Pressure relief, like I talked about, pressure is an important component when injecting liquids. And what we don't want to do is inadvertently fracture the formation and get uncontrolled flow. One of the things we've been doing for a while is putting pressure relief valves also on the injection system and giving them a set point of a maximum pressure not to exceed. So for example, if you don't want to exceed 50 PSI in a 30-foot interval, we'll set that pressure relief valve at 50 PSI. And if we hit that, it's going to send all the flow back to the mixing tank. So it's one way to control pressure. The other thing we do to control pressure is inner hose systems. So this way, as you add rods or remove rods through direct push, you're never breaking the seal between the pump and the injection tools. So you're not facing a situation where all of a sudden your tools are starting to plug, and then to unplug them, you've got to fracture the formation to get flow. So performance monitoring, these are key, obviously, to determining whether the injection went per plan. So pressure, flow, and volume measurements, how long the amendment is in the mixing zone or mixing tanks to make sure it's not reacting too quickly. Inventory and reconciliation. It's really a bad feeling when you finish an injection project and you have too much material left over or you don't have enough. And that's just not a place you want to be. Obviously, air quality is important with working with chemicals. There's digital and manual recording of data. Actually, making sure you're at the right depth is an important consideration. And then making sure you've targeted all the intervals and recorded data for each interval. And then actually where the boring locations are is also important. I see a lot of projects where the borings are never surveyed in, and if there's an additional event or 5 years later, a different approach, it's impossible to know where the injection occurred. So just real quick on flow meters. Typically the industry for liquids is using these turbine flow meters, and they have various ranges from 0.3 all the way up to 200 GPM, depending on the size. It's also very important that they're installed per the factory recommendations so that they're not affected by turbulent flow, which is going to give you unreliable flow measurements. Solids are measured through magnetic flow meters. You'll see these in some applications. They're more expensive, but they're preferred over manually trying to calculate the amount of solids injected by measuring changes in tank volumes. Or in some cases, we'll use weigh cells to measure the difference in weight of a solution injected. Pressure gauge is pretty standard, but make sure it's rated for the right pressure you expect. And if you need to have dual or triple gauges, if you think you're going to go through a wide range of pressures. And if you're working with solids, you got to prevent those from plugging, so you've got to use pressure gauge guards. One thing that we've rolled out is automatic flow and pressure control. So that's really getting away from these manual systems and being able to get a digital log of the complete injection performance and really eliminate some of the weaknesses we see with the manual control of ball valves, calibrating flow meters, plug flow meters. pressure gauges that break, and these systems can be used on single points or manifolded as well. So when it comes to drilling, obviously the size, strength of the limited access capabilities of the rig, whether it's track or truck mounted up. For manifold operations, typically you're going to need a track rig to be able to move around effectively. What kind of tooling you're going to use is important for distribution. Do you need dual capabilities with that rig, or do you expect that maybe you'll hit refusal and have to auger through some zones? Are you going to use an inter-hose system to control pressure? If you do, are you going to have to overcome refusal in certain zones? And then you're going to have to deal with the utilities and hand clearing. And hand clearing is often overlooked, but we've seen projects where hand clearing takes a life of its own. It actually becomes a critical path in completing a project. So just real quick on the tools, we've got the bottom-up retractable tools. So that sleeve covers the screen, you push the depth, and then you pull on that pipe and the screen opens up and you inject. So this is typically a bottom-up only method. The go-to that we've been using primarily is these direct push fixed open tools. And we have smaller diameter ones that we can't use inter-hose on, but they're in 1.5 and 1.75 inch ID. And then we have the pressure losses on these. So when you're trying to figure out what your downhole pressure is, these are generally the pressure losses you're going to see with water. This is the go-to tool we use a lot. This is the 2.25 inch fixed open tool. These can go top down or bottom up. We load these with inner screens to prevent them from plugging, either PVC or stainless steel. And in this case, we're showing the 5-foot tool, and we can make these in any length from 2 to actually 10 feet. And then also here you can see the pressure curves on these as well. And then sure, a lot of folks have seen these discrete hydraulic fracturing tools. They come in 2 sizes, 1.5 inch and 2.25 inch. You can use these top down or bottom up. It's important to note that most of these have check valves, and it takes 100 PSI to fully open that check valve. So you've got to factor that pressure into your overall pressure design. And you can see here on the right with the pressure losses at 15 GPM with water, that tool is fully open. And then as you get up to the higher flow rates, we see some considerable pressure loss as well. So just real quickly, how do you select the tool? Well, what we really want to understand is how the lithology sets up. We can do this pretty easily with MIP or MIHPT logs. And on the right, we have log, we have a clay over a sand, and here we want to go top down. So we always want to isolate the lower K material first. And then on the left, we have a sand over a clay, and here we want to isolate the lower K material first by going bottom up. So if you've got this extra level of definition of the lithology, you can make a more intelligent decision on what tool to use. And then there's just a little more pictures for the actually 2.25 inch inner hose. You see that's a high pressure hose on an injection tool. That's the drive cap. That's how we drive in the depth. And then on the right, that picture is of the a low pressure hose on a 5-foot fixed tool. Injection logs, important. Like I said, you want a project summary. So what happened on every day. We're going to want a detailed breakdown of what happened at each point and at each interval. Initiating pressures, average flow rates, pounds of amendment, dilution, water, etc. And like I said, with an automated system, we can automate this totally in terms of pressures and flows. But generally, these are the type of logs you need on a daily basis. And notes generally indicate something that may have impacted distribution, like daylighting or equipment malfunction or something like that. We're running short on time, so I have a whole discussion on shakedown, but you'll be able to download that in distribution testing. Troubleshooting. So just real quick, things don't always go right in the field, no matter how well we plan. So you need to be able to troubleshoot and work your way through these issues. This is just an example of peroxide daylighting. This is another example. The point here is, even though you have a fence at your site, you need to look over the fence to see what's going on off your site. And sometimes it might surprise you. And this is just shallow injection of calcium polysulfide for vadozone hexchrome treatment. So in a lot of cases, it's going to be difficult to keep those amendments in the ground at a shallow interval. I don't recommend injecting liquids into low-K material because you will get surfacing. This is an example of, sodium permanganate surfacing at a site, injecting at high pressure. So these are just recommendations that you'll be able to download for how to contract and what RFPs should address, so that you do get a good understanding of what you're getting from a contractor. So we can skip these. You'll be able to look at all these recommendations. And then my last slide is just going to be some words of wisdom. So these are just things I've seen over the years. If you hear yourself telling your contractor, just get it in the ground, your probability of success is low, because you're basically thrown out any concern over distribution and you just want to finish the project. You may not always get the A team or the A equipment on a project, because there's a lot of projects being managed by companies. And so, you need to plan accordingly whether or not you're going to have to provide more oversight. If you're doing direct push injection and you haven't done an optimization test, which we always recommend, always take a soil core first to verify lithology and set injection pressure and flow expectations. Hey, it's the interval sand, we go in and core, and it's very heterogeneous with thick zones of clay. That's a totally different project than what we planned for. The last day of injection is never like the first day. I mean, it's almost like the movie Groundhog Day. You got to really ride herd on the crew and motivate and set daily expectations to keep everybody engaged. And also, guarantees really are enforceable. So even though you might have a guarantee, don't abdicate to the contractor. You still need to be engaged, and don't count on the guarantee protecting you if the contractor doesn't meet expectations. So that's it. Thank you. We can open it up for questions. Sorry it took so long. There's a lot to go through, but I'm available.
Yeah, definitely a lot of great information. Thank you, Eliot. Just one last reminder, we do have the handouts available for download. And let's hit the first couple questions that came in prior to the webinar. The first, does Cascade have resources to help in the design of injection?
Yeah, we do. And that's exactly what I get involved in. We tend to focus primarily on the injection components of a design in terms of spacing, targeting, pressures, flows, distribution. We do have experience with the chemistries, and our focus is primarily related to residence time and persistence, especially when we're dealing with matrix back diffusion type issues. So we've seen a lot of projects. We know what works, what doesn't work. We've seen good designs, bad designs. So we definitely can support you in that. It's a collaborative effort, though. Where we don't say, here's what you have to do. We'll give you our best advice.
Great. The next question, regarding state of the practice for injections into fine-grained units, is it a waste of money?
I don't think it's a waste of money, but if you go back to one of our previous webinars of targeting dark matter, you really need to have a basis for how much of the transmissive zone you're going to target and how much of the low K zone or storage areas you're going to target. And that's going to have a large impact on the expectations you set. But we've had success targeting low K zones with different fracturing approaches over the years, and it can be effective. But it's obviously the thickness, the depth to the target interval, and how it relates to the transmissive zones. It's something that we have to look at in detail.
All right, thank you. Next question, what is Cascade's preferred method of direct push injection tooling? Expendable tips or expandable perforated inner rods?
Well, you saw those fixed open tools. That's pretty much our go-to because we can implement those top down or bottom up. We like to use the inner hose because it gives us much better pressure control and we don't have to worry about the tools plugging. Expendable points, really, we don't use those. I think they've been ruled out many years ago as not being very effective. There's very few cases where we may use those, and it's generally injecting like a solid slurry into a sand interval bottom up, where we know that as we pull up, the amendment's it's going to be easier to go lateral than back down the borehole. So that's our go-to tool, and generally we're in the 2 to 5 foot range on those, and we can be from the 1.75 inch to the 2 1/4 inch. And then obviously if we're fracturing, we're going to go through these pressure activated tools.
Thanks, Eliot. I realized we were at the top of the hour. We got 3 more questions that came in during the presentation, so we encourage you to stick around. Eliot, are you available to answer those last 3 questions? All right. So this one came. This one came in when you were talking about the pumps discussion. What is anaerobic dilution water, and what is the process for making the water anaerobic?
So, the best practice is that, back when you're doing anaerobic bioremediation, that, bacteria want to be in anaerobic water. And so what we have to do is take that water and make sure the ORP and DO meet certain levels to be conducive to the livelihood of the bacteria. And there's lots of different theories and approaches, but generally you can use amendments. Some of the substrate manufacturers provide amendments to help do that. There's sodium ascorbate, ascorbic acid, ZVI, lactate, dirt, nitrogen, pulsing in nitrogen. There's a lot of ways to do it, and it's really specific to how much water you need to turn anaerobic and how quick you need to turn it anaerobic. But it's pretty common, and a lot of our projects, we've got dedicated crew just to the anaerobic water aspect of the project.
Okay, the next question is about pressure relief. How do you determine the appropriate pressure to set a pressure relief valve at?
Well, if you're putting pressure relief on your pumps, it's got to be consistent with the pressure rating of the hose. So if we're using a high pressure hose rated at 3,000 PSI, generally we're going to be injecting high pressure, not a big deal. If we're using low pressure hose, generally the PVC hose can only withstand 250 PSI. So we're going to want to set it below that. If there's a pressure limitation for fracturing in a transmissive zone, then we're going to set that pressure either based on a design optimization test or on a rule of thumb in terms of how much pressure you can utilize before fracturing. And it's generally 1 PSI per foot of overburden, but you also have to take in account the hydraulic head that you'll have to overcome. So there's ways we can set that.
All right, and our last question for today. Are there permit injection well permits to factor into the project?
Generally, we're not applying for permits. So that is definitely, our client's responsibility. And so, there's 2 things that can slow us down. One is the work plan review. It was supposed to be done, didn't get done. There's access agreements that, are a nightmare for everybody that can delay. And then there's obviously the regulatory permits, submittals that have to be accomplished. So those are all administrative things that our clients have to deal with. And we just ask that they update and communicate with us accurately on that. So, nobody has to step back and remob at a later date.
All right, thank you, Eliot. Thanks for the presentation today. There's a ton of great information in there. And thanks to everyone out there in the audience for taking time out of your busy schedules to attend the webinar. I hope you did enjoy the session. A recording of the presentation will be circulated to all those in attendance in about a week. If you'd like to continue the conversation with Eliot, please don't hesitate to reach out to him directly. And as you log off today, you'll receive a very brief survey. We thank you in advance for providing feedback on the session, and we do read every survey. Thanks, everybody, and have a great day. We are signing off.